you would be asked to multiply it out. So Brandon, how do you think, there's a couple ways, how do you think we could come up with a polynomial function that has those zeros?
Well, I just went backwards, so I know it would be an x squared problem. So I just did x minus 1 squared equals 3.
Okay, so why?
Because since the zeros are 1 plus the square root of 3 and 1 minus the square root of 3, it would be x equals 1 plus or minus the square root of 3. Bring the 1 to the other side and then square it, and then you get x minus 1 squared equals 3. Bring the 3 over to the other side. F of x equals x minus 1 squared minus 3.
Okay, so I don't know if you're following along with what Brandon said very quickly. So he looked at it as both of these x-intercepts as combining them as one solution. Because if we were completing the square, that's what our solutions would look like. So we have x equals 1 plus or minus the square root of 3. He then took the 1 to the other side so that it was next to x. And that would give you x minus 1 equals plus or minus the square root of 3. And he said he worked backwards. So if you're working backwards, the goal is to get that square root of 3 out of the problem to kind of get everything together on one side. So if you square both sides, then you end up with this piece right here. And then he said he took the 3 to the other side, and then that's considered the standard form of a quadratic. However, if there was a third 0 there, if it said that you had a 0 at 0 as well, we would have to place that x in front and continue to multiply and FOIL the problem out. So if you multiplied this problem out, you would end up with x squared minus 2x plus 1 . It shouldn't be plus 4 though.
It's because
What if
it's subtract 3.
Oh, thank you. This here is a minus 3. Okay, thank you. I knew something was off. There we go. So we have to subtract 3 to get it next to the other side. And then the final answer could be x squared minus 2x and then minus 2. That looks better. So that could be one solution. We could change that solution by having an a value of 2, and like if we wanted to, we could put a 2 in front here and then multiply everything by 2 if we wanted to. So that would kind of change the answer. Questions on that? So as Brandon said, like work backwards. If that's your answer, how can you kind of arrive at an initial problem? So if you started with this, if this was given to you, you would complete the square to solve it because you can't use factoring, or you could use the quadratic formula if you prefer to do that. Like if this is where we started, we would have to complete the square to get to the x-intercepts. It's kind of just like working backwards through the problem.
I like those problems.
Yeah, so you do them one way and then you kind of flip them around and go the other. The other one I wanted to talk about was number 110. That was the box problem. So an open box with locking tabs. So that pretty much means that like you fold them. Think of like a box, like a shirt box at Christmas, like that kind of thing, where the tabs lock together. So that's kind of what we're talking about here, except this box has these little extra pieces that fold on the top of two sides. So it says this box is made from a piece of material that's 24 inches on each side. It's done by cutting equal squares from the corners and folding along the dotted lines as shown. And then you have that picture over here of what your little box should look like. Part A says to verify the volume of the box is given by the function v of x equals 8x times 6 minus x times 12 minus x. Verify is a nice word for saying prove. So the goal of part A is to figure out how the heck they got that equation. Where did it come from? How did the information in the problem dealing with 24 change to be 8x times 6 minus x times 12 minus x? So that's the goal. If something says to verify, we need to figure out how this equation was created. So what part of the initial problem created that? And just to kind of talk about that, boy, all my papers have writing on them. If you look at the box, and I made my own box. So here's my own little box. It says that you fold up the corners of the side, and it has drawn on there that each one of those folds is a distance of x. So we have a length of 24. This is my 24-inch piece of paper, even though it really isn't. And then we fold it up and fold the side over, and now I have this new distance to make the box. So we started with 24, but once we do a fold for the side and this little extra fold over, the new space, this space that's right here, like, what space is that left? What is the distance of what's left over after we do those folds? So that's what we need to think about. So Brandon, what is that distance after you do the folds?
24 minus 4x.
So that would be the length. The initial length is 24 of the piece of paper, but once we start folding it to get a side and to get the little piece on the top, we did have 24, but we took away 4 x's, 2 x's to be the top, 2 x's to be the sides. So that's why it's minus 4x there. And then if we look at the width, well, the width is also 24 because this is a box. So doing the same thing, if we fold up just one side, because this piece, the width doesn't have the little leftover portion on the top, so it just has the height of the side. So we would take away 2 x's for the width, because there is no top little flap that goes on the top. So that's why it's 24 minus the 2. So the one distance of the width is actually longer than the length. And then what's the height of the box? How high is it? So if I have this box, what is the height of that side? Brandon? X. I'm just going to place that x in front because it's just a single term. So the volume is equal to the length times the width times the height, which we found by taking 24 minus the 4 x's that were used to fold up each side. And then the width would be 24 minus the 2 x's because it just has those two sides. It doesn't have the little lip on the top. And then if you simplify this, what can we take out of the first set of parentheses? 4. And that makes 6 minus x. Virginia, what can we take out of the second set of parentheses? A 2. And that makes 12 minus x. And then if we multiply the stuff that we pulled out together, that's how they came up with the 8x. The 6 minus x, the 12 minus x. So that's a proof. Believe it or not, that's an algebraic proof. Not what you think of in geometry. Totally different. But that still is a proof. You verified how that equation was created by using the information you were given about the original box. The next part, so this is A. B wanted you to get the domain. So using what you know about objects. If we have an object, what can't the domain be? Of any shape. It can't be negative. It can also not be 0. Because if it was 0, I still wouldn't have a shape. So the domain would have to start at 0 but can't include 0. And then again, remembering that volume is length times width times height. This equation represents the length, the width, and the height. So it represents the size of our box. So that puts a restriction on the domain because I can't have a side that is negative. So what's the longest side that we could have to plug in for x, keeping those quantities that are in parentheses still being positive? Michael?
Would be a 6 with a bracket,
It-
or not a parenthesis.
It would be a 6 with a parenthesis. Because you can't take 6 minus 6, because this side then would be 0. But I could do 6 minus 5.5, 6 minus 5.4, 6 minus 5.9. We just have an itty-bitty little box. So that's how the domain was created. So thinking that each one of these represents a length. You can't just plug anything in for x if it's specifically talking about a box that we're trying to create, because we only have so much distance to work with. There's only 24 inches to begin with. And then the last part was just graphing it. Questions? So you'll see that problem 2 times. One, it's on the application worksheet, page 21, which isn't due until Tuesday. I erased that from the board. But in your packet, page 21 is very similar to this. Not identical. A couple of the questions are different. But that is due on Tuesday. I'll be collecting that. And then you'll see it again on the midterm exam. And I'm telling you now, so maybe you'll put a reminder that you won't throw that piece of paper away, and you'll remember on the midterm instead of spending like 15 minutes on it and not being able to finish the midterm exam. Free question on the midterm. God bless you. Questions? Okay, so there's one other problem that I want to do, but I want to do it in the notes with you. So in your notes, if you can turn to page 19. Yes, you can put that's due on Thursday. That would be awesome, Brandon.
Sweet Thursday.
Not Tuesday, sorry. Today's Thursday. Tuesday. And I actually want you to take out a calculator. We're going to use a calculator as well. You and Jesse. Jesse lost his too. He must be a calculator monster that comes into your room, steals your calculator.
Well, they are worth a lot of money, so you could probably make a lot of money off of them.
All right, so the intermediate value theorem sounds really fancy and complex. Intermediate is another way of saying middle. Yeah, intermediate, middle, they kind of go together. So we're finding the middle value up to given points, or a value that's somewhere in between. It doesn't have to necessarily be smack dab in the middle, but it's going to be somewhere in between 2 points. So the wording of this is pretty crazy, but it really doesn't have to be as complex as it sounds. So if f is a polynomial function, remember polynomials are continuous. They go on forever. So looking at this graph, this is just a weird graph, but it doesn't have any breaks in the graph. It just moves on. Such that f of a doesn't equal f of b. So that means you have y1, which this should be down a little further, but here's y1 and that's y2. 2 y values on the graph. Then in the interval a to b, so I have an x value of a, we have another x value of b to kind of match up with those y values. Every value in between f of a and f of b has to exist. That's the definition of a polynomial. So essentially, some math guy created this, and he came up with the intermediate value theorem. But all this is saying is if you pick 2 points, in between those 2 points is going to be at least 1 point in the middle. Now it's going to be infinite because there are a whole bunch of points in the middle of 2 other points when you have a polynomial.
There's infinite answers and then there's infinite wrong answers.
So I guess that's true too. But what we're going to be looking for is one specific value. And that says here that if I have a value of d, then it would be equal to a height of f of c. So again, that's just saying that there is another point in between 2 points if it's a polynomial. And I'm going to show you how that works with regard to a problem. If you take AP Calc next year or some other time, you will go more in depth with the intermediate value theorem. You'll work through and do a proof with the intermediate value theorem, and you'll start using it with other concepts. But right now, we're going to focus on one concept, and that's the concept of a zero. Because that's what we're talking about right now, polynomials. So if you look at the example underneath, use the intermediate value theorem and a calculator. So I'm actually telling you to use technology to find intervals of length 1 in which the polynomial is guaranteed to have a 0 or an x-intercept. That's what a 0 is. So length 1 means that interval from a to b. This interval from a to b has to be a distance of 1. So like from 8 to 9 is a distance of 1. So we're going to find an interval that has a distance of 1 where there's an x-intercept in the middle of that interval, because the intermediate value theorem can help us find x-intercepts. The reason we need the intermediate value theorem to find x-intercepts is because every problem isn't factorable. Only some problems are factorable, but not all of them. So a problem like 12x cubed minus 32x squared plus 3x plus 5 can't use AC grouping because it's not a quadratic, or it's not a trinomial. Factor by grouping doesn't work because you can't really group the first two together and the second two together and get it to factor in any other way. So factoring isn't an option, the quadratic formula isn't an option, completing the square isn't an option. Right now we don't have any other option besides to rely on the technology. So in your calculator, if you can plug this in, and I want to show you why the intermediate value theorem is a little bit helpful for us to kind of use with the technology that we have. Next week, I'll show you how to use it without the technology, but right now we're going to work on what we have for our technology. So that 12x cubed minus 32x squared plus 3x plus 5, hit graph. You get this graph here. You don't need to zoom in. If you were zoomed in, hit zoom 6. That takes you back to the standard screen. So our goal is to look at this. How many x-intercepts do you see? 3, because it was x cubed. Crosses the x-axis 3 times. We need to pick two numbers that would essentially trap an x-intercept in between those two numbers. And the easiest one to see is over here. So what two numbers would this x-intercept be in between? Alice? 0 and 3. Okay. How about give me two numbers that are even closer together, Alice, that are only 2 and 3. There we go. That's all right. So 0 and 3 works, but we want the distance between them just to be 1. So 2 and 3, in between those two values, has an x-intercept. We're going to use that in a minute. Can anybody give me another set of values with a distance of 1 that has an x-intercept in between them? Chelsea? 0 and 1. In between 0 and 1, there's an x-intercept. It's pretty close to the y-axis there. And Brandon, another one would be?
Negative 1 and 0.
So those are our intervals of length 1. So you're looking at the calculator, you're saying this is an x-intercept. It has to be in between 2 and 3. We don't know what it is, but I know there's 1 in between there because it crosses the graph. Based off the intermediate value theorem, there has to be 1 there if it's a polynomial. So here's where the calculator is pretty cool. We're going to find that value by using second trace and going to the 0 function of the calculator. So we're going to hit number 2. But instead of moving that little blinking guy so that it's at the 0 or close to the 0, we're going to use the numbers that we chose for the intermediate value theorem. So you're going to type in a 2 because that's on the left. Hit enter. Type in a 3 because 3 is on the right. Hit enter. Never do anything for guess besides hit enter. And now the calculator has found that 2.5 or 5 halves is an x-intercept. Do it a second time. Do it a third time. So find the other 2. If there are 4 of them, you have to do it 4 times. So you get 4 different intervals with an x value being in between those 4 intervals. So right now, the intermediate value theorem is for us to kind of see where is there an x-intercept, what 2 numbers is it in between, so we can get that calculator to help us find those values. So in between 0 and 1 would be, is that the one that's 1/2?
Yeah.
So 1/2 and 0. And then in between negative 1 and 0 is, I think it's negative 1/3. Questions? That's what number 95 was asking to do. No, we didn't get to it yesterday. I think some of you actually still found the zeros on the calculator. We just didn't get there yet.
We don't have to do it without the calculator.
We'll talk about the rational zero test next week, Brendan. Then I'll show you how that works without a calculator. I promise. As much as I can do without a calculator, we'll do. There's still some things that you won't be able to do till next year. So today's homework is different than what's on the assignment sheet. The assignment sheet has bookwork, and instead of doing bookwork, we're going to do a little review worksheet on section 2.2. So on the front of this page are 4 problems where you'll find the end behavior. The zeros algebraically make a little sketch of the graph. If you want to sketch it on here, that's fine. If you want to sketch it on graph paper, that's fine as well. Okay, that's kind of up to you. And there's a couple pieces of graph paper over next to Kayla. I didn't realize that I was out of graph paper until 3rd period. and then I just haven't been able to get to the copying machine. The last thing you'll do is get the max and the min to finish the graph. If you make a sketch on here, please make sure you're making little tick marks at least so that you're still plotting points accurately. On the back are two problems that you'll have to find the given polynomial based off of the zeros. Please multiply that out. So actually do the multiplication, don't just leave it as x plus 1 times x plus 2. 6 is just factoring to find those zeros, you don't have to graph those. And then 7 is the intermediate value of 0. So you have about 8 minutes, which at least gets you to start. I will tell you that after you factor number 1, you're going to have to use a really nice formula.
Like that.
Or you can complete the square. But you'll have to use that for number 1. So it is factorable. There's a GCF. But after you pull out the GCF, it doesn't break down any further. That's just. So if you want to work with somebody, you can. Again, you have 8 minutes, so you might be able to get a problem done, another problem started, or maybe you just want to work on like part A of all of them, A and B,